Welcome to today's lesson. Today we're going to continue with solving trigonometric equations, part 2. So we're going to look at some tricks of the trade to try to solve slightly more complicated trigonometric equations and see if that helps us get a little further ahead. First of all, I have an example here, and it says 1 plus sine x equals 4 sine x. So we have a nice little trig equation, and x is between 0 and 2 pi. So I'm looking for a specific answer between 0, including 0, but not including 2 pi. You'll notice also that when you see the 2 pi, that tells us that we're not working in degrees, but rather we are working in radians. So the answer is expected to be in radians. Well, here's what we do. This is an algebraic approach, and the first thing I think I can do is subtract sine x from both sides of the equation, and that will produce 1 equals 3 sine x. Okay, by subtracting 1 sine x away from 4 sine x's, we're left with 3 sine x's. Well, let's isolate that sine x. We're going to divide by 3, so we get 1/3 is equal to sine x. And at this point, I can't give an exact answer for x because 1 and 3 are not any of the two sides of our special triangles. So what am I left to do? Well, I'm left to take my calculator and take sine inverse of both sides of the equation. So what I'd end up doing here is sine inverse of 1/3, and over on the right side, sine inverse and sine cancel each other out, and that leaves me with x. So this becomes something that I would do on the calculator, making sure that it is set to radians. I've done that in advance, and I got this as a result. 0.3398. A very nice radian angle. So this would be one of our solutions. Now, it's very common for people to think, that's it, I'm done, I've done my solution. However, in just about all cases, there is a second solution, and we have to go and find that second solution, and in order to find it, we use an old friend called the cast rule. Now, if we look at this trig equation at this stage of the game right here, we have a sign that's positive. 1/3 is a positive number. So we know that our answers should be in those two quadrants. And as for 0.3398, as to which quadrant that's in, and these are very rough approximations, but we know in radians that it goes 0 to pi. Now pi over here at 180 degrees is something like 3.14. And half of that is something like 1.6. Now that's again a very crude approximation, but it tells us that 0.3398 is in the first quadrant. So I'm just going to pretend it looks something like that. So what we have is a reference angle, and we're going to use that reference angle in the other quadrant. So that means the other quadrant, we're going to envision our reference angle down there. And how do we name this angle? Well, we want to go from here to there. In other words, the supplement to our reference angle. So what we want to do is take pi, which would be the equivalent of a straight line, and subtract from it, or back it up, by 0.3398. So the other solution is 2.8018. So these are my actual two solutions, not just one solution to our original trig equation within this restricted domain. So that's our first example. Well, let's do another one. Clear off the board. Do one more. maybe even 2 more. Okay, in this example, I'm going to try and find exact roots for the following. 2 times sine squared x minus sine x minus 1 equals 0. And again, I'm going to restrict the domain and say, let's work between 0 and 2 pi. Now you will notice that this equation has a very quadratic kind of look to it. I mean, in a sense, we have something squared minus that same something minus 1 equals 0. So what we like to do here is treat it like a quadratic equation, which means that we could go to, say, the quadratic formula, or maybe even factoring. And I'm going to try my luck at factoring this thing. Suppose I tried to put it in this form where I had 2 sine x, and let's see, then we would have a sine x over here. And so what I need to do is say, well, how could I get negative 1? Well, the only way I could get negative 1 is a 1 times a 1. Now, one of them has to be positive and one of them has to be negative. But I want my middle term to end up being negative sine x. So I have to experiment a little bit here. This is going to produce a 1 sine x, and this is going to produce 2 sine x's. So I want this one to be negative, so that I get negative 2 sine x's, and this one to be positive, so that the combination of the two makes negative sine x. Okay, so it does factor. If it didn't factor, I could have gone and used the quadratic formula. Heck, even if it does factor, I could have used the quadratic formula. But in any case, I'm off on and running here. So 2 sine x plus 1, I would like to see what that would be if it equaled 0. And so I could bring the 1 over and then divide by 2. So it'll look like this. Sine x equals negative 1 divided by 2. Now this is an equation that I can solve for x. But before I do that, let's do the other one as well. To make sine x minus 1 turn into 0, we would like sine x to equal 1. So I kind of have 2 equations on the go here. And so now I'm going to think about, well, how do I solve these 2? And does any of them work in, say, my special triangles? Well, this one does. It makes me think of a special triangle that looks like this. In this special triangle, the sides are 1, 2, and root 3. And there's our right angle. Now, in radian measure, the angle that we want is this guy up here, because we want the sine to be 1/2. Now, I know it's at negative 1/2, but I'll deal with that in a moment. In order to get 1/2, oops, I see I've written this backwards. Much better. In order to get a sine of 1/2 for this, of course, I want this angle up here because opposite over hypotenuse gives us 1 over 2. So the angle up here that I'm interested in is pi by 6, also known as 30 degrees. Now, this angle, of course, is not a solution because this angle produces a sine of positive 1/2, but we want negative 1/2. So in order to solve that, I have to look, using the cast rule, at which quadrant I need to be in. I want a sine that's negative. So I have to be in this quadrant and this quadrant. Now, you might be saying, well, where does this pi by 6 come in? Well, this is our reference angle. So we construct it in the 2 desired quadrants. The reference angle always constructed from the x-axis. So here's our pi by 6, and here's our pi by 6. all I got to do is name these two angles, and I've got two solutions. So how do I name them? Well, some people have different methods, but I think the easiest thing, and it seems kind of a little bit like counting on your fingers, but I think it worked quite well. To go from here to pi, I'm going to kind of subdivide everything into sixths, so that it goes 1/6, 2/6, 3/6, 4/6, 5/6, 6/6. Okay, so that brings me to pi. And then I want to go one more. So that's going to be 7/6. So I'm just going to write that over here. Okay, so that's 7/6. And then I can go 8/6, 9/6, 10, 11. So that's the other one. 11/6 pi. Now there are ways, if you don't like that, you could do something like pi plus 1/6 pi. Yeah, that works too. Or you could do, for the other one, you could go, a full rotation is 2 pi, and then subtract 1/6 from it. I like the counting on the fingers method. Works for me. So here's what we got. Two solutions, and that was using sine x equals -1/2. Okay. Now I'm going to need a little room for this guy here. This doesn't look like anything from a special triangle, but what it does look like is maybe the graph itself. So we'll make a little space here and ask ourselves, when does sine equal +1? So let's just look at the graph. That's, I think, the easiest way to identify when does sine equal +1. Well, my goodness gracious, right here. Well, what is that guy? Here's the 1. That's when sine equals +1. And this is 2 pi, remember? And this is pi. So this is pi by 2. There we have it. That's the missing solution. Pi by 2. It's just that much fun. Okay, so we got 3 solutions here. I'm going to do one more example. And in this example, there's another little trick of the trade that creeps in. And then I think we've done enough solving of these things for now. I'm not saying I'm totally done solving, but for now, I think we've solved enough. Okay, for this last one, I think what we're going to try and solve is sine x times tangent x. And we're going to have that equal to sine x. Okay, and we're not going to say specific domain. We're going to try and solve all of them, the general solution, in other words. Okay, well, I look at this thing and I go, well, it's very interesting. How about we bring the sine x over to the left side so that it equals 0? So that might be a good start. Sine x times tan x minus sine x equals 0. And of course, these things are kind of cooked up to work for you. There's a sine x that's common to both of these terms. I'm going to factor that guy out of there. So here's what I have. Sine x times tan x minus 1. Well, how about that? So now I could use my 0 property and say, well, I need sine x to equal 0. That might get me some solutions. Whoops, equal 0, yes. And I need tan x minus 1 to equal 0. In other words, I need tan x to equal 1. So these are my 2 smaller equations that I can now analyze. Well, sine x equals 0. When does that happen? Let's look at a graph of sine x. Oh, there it is at 0. There it is at pi. And there it is at 2 pi. So it seemed pretty clear from the graph it is happening in multiples of pi. Multiples of pi, where n is any integer. Hey, that wasn't so bad. Some might say it was even fun. All right, let's go to, when does tan x equal 1? Well, luckily we've memorized the graph of tan x, but even if we didn't, I think there's a special triangle that could help us out. And that special triangle looks like this. A very squeaky pen tonight. 1, 1, and root 2. So the tangent of this angle seems to be doing the trick for us. It's going to be 1 over 1. And that angle, of course, is pi by 4. Now, in conjunction with the graph, which I think is very helpful in confirming whether or not there are other solutions, I'm going to have a quick peek at the graph and just have myself a little look. So the graph of tan x looks something like this. First of all, the period of tangent is only pi, and at pi by 2, there's a vertical asymptote. So we have a graph that does this. It goes roaring up to infinity, and then kind of comes roaring back up on negative infinity. So if we look at one period of this graph, and let's say this is the y value of 1, it would occur in only one point during one cycle. So all I have to do is say, well, I know what that one value is. That is occurring at pi by 4, and I'm going to add to that multiples of the period. Again, n belonging to the set of integers. Well, the graph confirms it. There are my solutions to this trigonometric equation. Pretty neat stuff, I have to say it, even if it's just me saying it. We'll catch you later.